Okay, so we're going to start chapter 6 by looking at polygons and their angle sum. So our first theorem, polygon angle sum theorem, goes over the interior angles. So the sum, the measure of our interior angles, of a polygon, so a many-sided figure, polygon, is the expression n minus 2 times 180, which just means that the number of sides, n, of our polygon minus 2 times 180 will be the sum of our interior angles. And we're just going to add a couple names in here for our polygons. Some of these are familiar. Three-sided polygon is a triangle. Four-sided is a quadrilateral. We've got a pentagon for our five-sided figure. Got a hexagon for six-sided. Hexagon. Skipped a couple things. And then a heptagon for seven sides. That one's a little unfamiliar. Octagon for eight-sided. Nonagon for 9, 10-sided. Decagon. All about the prefixes, really. 11, anything that we're not going to spend too much time on. 11 gone, 13 gone, things that we don't have a name for. We'll just put the number of sides. And then 12 is dodecagon. Okay, so these are some vocab that we'll need. Finding the sum of the angles is going to be based on knowing how many sides we have. So a quadrilateral, that's 4 sides. What that means is n is equal to 4. So I'm going to take the n minus 2 times 180 and put in 4. So 4-sided figure minus 2 times 180 means that I'm going to get, and I always want to just do the parentheses first, so it's 2 and 180. So any quadrilateral has the sum of 360 for its interior angles. Next, we'll do the hexagon. So it's still going off of the n minus 2 times 180. And a hexagon, that one has 6 sides. So n is equal to 6. We get that info from the name. So it's 6 minus 2 times 180. So we'll get 4 times 180. And so a hexagon, sum of the angles, interior angles, is 720. Heptagon, we've got 7 sides, so n is 7. So 7 minus 2 times 180. So 5 times 180 gives me 900 for the sum of the interior angles. Some important language also. Equilateral. We know equilateral, same sides. All the sides of our polygon are congruent. We talked a little bit about that with our triangles. All the sides are congruent. Equiangular, equal angles, right? So all of our angles are congruent. And we're going to have a special term for polygons that have equilateral, equiangular, that are equilateral and equiangular. So we'll write that. So all the sides and all the angles are going to be congruent in a regular polygon. We're going to be dealing mostly with regular polygons. Little corollary to our interior angles. If we're working with a regular polygon, each interior angle of our regular polygon, because they're all the same, is going to be able to be found using what we found before, the n minus 2 times 180, and then divided by the number of sides, n. So this is to find each interior angle. Before we were finding the sum, so the total, now we're finding each. So if I have a pentagon, I know n is equal to 5, and that's going to help me find each interior angle in this regular pentagon. So it's 5 minus 2 times 180 divided by 5. And we'll get 3 times 180 divided by 5, and we'll get 108. So each interior angle, so if I have a pentagon, see if I can draw it, and supposedly this is a regular polygon, so if I draw on it, each of these angles here would be 108. I did not draw it as a regular polygon, so that's, I think, the main issue.